Okay. Okay, so for those that just just joined us, I want to repeat, if you haven't taken the buffers quiz yet, hold off. If you've already taken it, then there's nothing I can do for you. I did advocate for one more attempt, but Richmond was very adamant about 2 attempts being fair. So do not take the quiz yet, because today I think that people are having a lot of issues with the content that he's posting, and trying to understand these little PDF Word documents that he's putting together. It's a lot of just reading jargon. So I think what we'll do today is we're going to go through, I feel it's in our best interest if we work on acids, bases, and buffers. If you already took the quiz and you got a poor score on it, there is nothing more that I can do for that. I already tried to ask him to give 1 more try instead of 2 tries, 3 tries, but he's adamant that that he thinks it's fair and there's nothing more we can do about it. I also talked to him about it, that unfortunately, you know, he said that the quiz was going to be due Wednesday on the 1st. I think there was a memo saying the quiz was going to be due that Wednesday, and then he changed it to be April 4th. Go. Okay, no, I'll get you one in a minute. Go. I think what happens is I talked to him about how he said that the quiz was going to be due April 1st, which was Wednesday. And then the due date's actually April 4th. So I feel like some people felt rushed or obligated to take the exam quickly. Again, I presented that to him and still no budging. I think he might reconsider, but the chances are looking very slim. So it's only worth 6 points. So like I said, if you did poor on it, just know that that's something that we should focus on, because that's going to be the exam, okay, for Monday. So what we're going to do now is we're going to work, instead of working on the review, which is math, and we hit that hard in our last review, I feel like you can go through and kind of relook at that YouTube video to do some more molarity. But I feel like we need to hit acid base, because I think people are really stuck on this, and buffers. So today is really just going to be acid base, buffers, pKa, and the math that kind of associates with that. If there's any objections to that, just go ahead and send me a message, and we can try and change and do what you want. Okay. So
quick question.
Yes.
So are we not going to go over percent mass anymore?
Yeah, we are doing percent mass as well.
Okay, perfect. Cool.
That's a super easy one to kind of go over. So we can start with that one too.
Okay, thank you.
You're welcome. So let's see. Let's see what question I have. That's a good one. Okay, so we'll start with, let's see if I can get this working. Okay, so let's go ahead and start with a mass percent. So I'll title this mass percent. Okay. All right, let's see. Okay, so a mass percent problem. These are kind of, so a question could say, calculate the percent by mass of a solution prepared, and then by dissolving. Okay. More people are coming. Okay, so by dissolving, where's my, sorry guys, I have to admit all these people. Okay, by dissolving, let's say we'll say 5.40 grams of CH3COOH in 75.0 grams of H2O. Like I said, most things will be in water, since this is more of an acid-base chemistry test. This is going to be the acid-base focus. So everything that he gives you is going to be dealing with water. So be familiar with water, be familiar with hydroxide, because that can form water. Those are very crucial things. Okay, so in this, let's just start it conceptually. This kind of problem, I like to treat it as a pie and a piece of the pie. Okay, so when you're starting to do percent by masses, the whole thing would be equal to what you're dissolving. So this is A, what you're dissolving, plus B, which is the whole thing. You're doing it in water. So the equation is what you need to dissolve on the top, or what you're dissolving goes on the top, and then what you're dissolving plus the solution goes on the bottom, times that by 100%. So in this case, we're given 5.40 grams. So that's going to go on the top, and that is just of the CH3 COOH, right? So that's the piece. This piece would be the CH3 COOH, and all of this would be the whole pie, including the CH3 with water. Okay, does that make sense? So then down here, you're going to have the whole amount, the entire amount together added. And they're both in grams, so we don't have to do any kind of conversion. So once you do that math, you go ahead and just times that by 100%, and that will give you 6.72%. And that's the mass of the CH3 in water. Okay, and that's all percent mass is. Take the piece, what it is that you're dissolving, this part right here, what it is that you are dissolving in the whole solution, which makes sense to account for it, and then we're going to see how much this takes up in solution. Okay, so that's all percent mass is. Just doing that. Okay, any questions on that stuff? Those are what the problems will look like. Go ahead.
So if it's not like both grams, you just convert it and then do that?
Yep. And so you could see things like he might trick you and give you 1 in milliliters and 1 in liters. So you can convert this to liters just so you get the same kind of decimals, right? So, but most of the time you don't have to do any sort of conversion. I've never seen him give kilograms to grams, do kind of that thing. But as long as they're in the same, it makes the math easier. Oh, more people. Okay, so like another one, let's go ahead and, what problem are we on? I am just doing a bunch from his past exams. So those, I still am working on our review sheet. So there's 1% mass on the review sheet that I made for you guys, but a lot of these other ones are just gonna be from past exams, which I know he'll probably reuse. Okay. Let's go ahead and do 1 more percent mass. So if we have 2.5 grams of KCl, and we're putting that in, man, another person, okay. And we're putting that in, let's say this is on the homework assignment, or on the assignment that I guys sent you, the practice review, and we're putting that in 50 mils of a solution, and he could just say of solution, all right? No, you're good. So then what would we do? We're trying to find the percent of this, because this doesn't have a definition. He's just telling you the solution, right? So KCl is the mass that we're trying to find of the whole total. That's my kid. Hold on. Lou, hold on a second, bud. Okay, good. Go play. Okay, give it to me, my minion. Okay. I'll open the cheese, and then will you go play on my bed? Okay, I got it. Don't worry. Bye. So then again, we'll do the same thing. We're trying to find the percent mass of the KCl. So we'll put that right here, and we'll put this 50 mils. We have to add the volume to the grams. So 2.5 grams plus 50 mils. And then you can go ahead and find that math, and don't forget to multiply it by 100 to get the percent. Okay, that's all you're doing. You're adding those two things together on the bottom. That is the key focus here. Most people just do 2.5 divided by 50, but that is not going to account for the entire solution. We're seeing that, okay?
Do they not have to be the same measurement?
Well, this is a liquid, and this is the mass, because we're finding percent mass, so we can't turn a liquid into a gram. So you can still have a gram over a liquid, because this is just a quantity in this case. But when you have like other things, if you were to say we have 3, let's do a box here. Say there's a problem and he gives you KCl, NaCl, and solution. And your solution here is 75, it's 75 mils. But if this one, this is a typo, he should have put, it doesn't matter for that. But oh my God, I got a new tablet thing and it does this all the time. Look, it's like why is it doing that? Stop. Okay. So if he gives you this, these two, if this one was given to you, it would, which it would never be, if this was given it to you here and this was given it to you here, you would want to change this. But really we're just adding. How do we take 50 mils and turn that into grams? How would we do, how could we do that? Can we take a liquid and put it in terms of grams?
No.
Right? So that, it doesn't really matter for that.
So like, is that the same? Because like on question 8, that's the one that you were doing. With a 1 liter solution containing 25 grams, it'd be the same. Like you wouldn't have to convert grams to liters. Okay.
No, because the grams are the solid. So you have a solid KCl, and the grams mass is usually for a solid, and milliliters, liters are for liquids. So in this case, it doesn't matter. You're just given a whole solution. I would just change things if you were given 2 solids and they were in different units. But I've never seen him do that. So then for your bottom value, you'd have to add this plus the solution amount, and then divide out just to find the percent of KCl, right? That's all we're trying to do is just find one thing. The only thing that have to match is like with like. So if you have 2 things that are dealing with mass, 2 things that are dealing with mass, they both have to be the same. They both have to be the same unit. Volumes, same thing for volume. If you're given 2 volumes, 1 in milliliter and 1 in liter, convert these to be the same for both. Okay? Is that more clear? Okay, so percent mass is relatively easy. There might be just one question on that. Let's go ahead and just do a brief micro lecture on acids and bases so that everyone kind of has the gist, if we're okay with that. Okay, so we'll just do a quick micro lecture and then we'll move into some practice problems. So the biggest thing that you want to deal with that you have to talk about is weak acids, weak base, conjugate acids, conjugate bases, etc. So the biggest thing here is you'll have like H, A can go into H plus A minus. So this right here is denoting your acid, okay? And so then you'll have to figure out what is conjugates and what is conjugate acids and conjugate bases. So a good example that I like to do, because people like to actually see stuff, is, and mind you, this is always with water. Okay, so acid-base chemistry will always start with water and some acid to dissociate. So in this case, this serves as the base. And then over here, we have one source of hydrogen, right? So that's what we've told you, like most acids have are hydrogen bonding because they have one hydrogen here. So if you are an acid, okay, and let's just say we have HCl, what's a good one? I won't do that yet, let's wait. So because this has one hydrogen and that's why we denoted HA, so this will be our acid. When we take away an hydrogen, any sort of hydrogen gets taken away, it's gonna look like this now, right? So follow your similar things. So HA will go in turn, if we lose an hydrogen, it's gonna become just an acid. If this was once the acid, now we're gonna call this a conjugate base. Okay, and the reason we call it a conjugate, oh God, that's horrible. Okay, still learning guys. We're gonna call this the conjugate base. The reason is it's a base is because now it's missing the proton source. So it's no longer acidic, okay? That's the goal that you need to understand. You were once an acid. The opposite of being an acid is a base, and it's conjugate. It's a conjugate, just meaning opposite, okay? Here we have H2O, right? And if we're gonna turn this base into an acid, we'd have to add hydrogen to it, right? Because that's what's losing here, and these two things are interacting, okay? So if we lost a hydrogen and now we're here, you have to think about in solution, now I have a free-floating H and I have water, okay? So these two are gonna interact and we're gonna turn this into H3O plus. And now here, we are now a conjugate acid, okay? Because water was once a base, okay? And now we've turned him into an acid because we've protonated him. So some things that you need to learn are protonation. And all this means is to add H, hydrogens, okay? A hydrogen ion. Deprotonation is removal. So in this case, this acid was what? Protonated or deprotonated?
Deprotonated.
This was deprotonated because it turned into this. Deprotonated, okay?
Mm.
H2O, our base, was what?
Protonated.
Protonated. Why? Because all we're doing are adding or taking away hydrogens. That is the key to acid-base chemistry. Following acid-base chemistry, I'll put acid-base chem equals follow H plus. Okay, that is the biggest thing. If you have protons, you're more acidic, okay, in the circumstance. So let's go ahead and erase all this and we'll learn, we'll do some examples here dealing with writing chemical reactions. So say he gives you a weak acid, and that is HF, okay? And so first things first is, what is the conjugate of HF? And would it be a conjugate? What is this? I already told you it's a what?
Acid.
Acid.
Okay, so what is HF's conjugate?
F minus.
F minus, okay? This is the conjugate what?
Base.
Base. Good. Now, what I want you to do is, then he'll tell you, we're gonna we need to add a buffer, or we're gonna show how this buffer can remove added hydroxide from the system. So he's telling you that there's OH, that's OH is hydroxide. He's telling you that there's hydroxide in the system. Remember, everything acid-base deals with water. So if we're starting to write a chemical reaction, we have OH in solution and we have our weak acid, okay? So I've already told you that even if it's weak, you don't have to write weak. In general, this is the acid, so then what is this?
The base.
The base. Okay, and you've already told me that the conjugate base is F minus, so what would be the conjugate acid? What's going to be H2O? Yes. Okay. Why? Because this came here, which means we have free floating of this, which means this minus picked this up and created this. We did not gain anything extra. We're using what we have in solution. Okay. So when you're doing these equations and you're writing things out, conjugate base, acid, acid or base, you need to understand that you should not be adding anything else into solution. Everything is in water, so you have a generous amount of this in solution already, okay? Because that is this, right? So anytime you see hydroxide and an acid, note you're going to make this product, okay? If you have this on the left side as a reactant, okay, note that you'll probably make H3O plus, right? Because if it's on the left, if water's on the left side, the reactant side, most times it's going to be serving as a base, okay? Most times. Because you'll have something already acidic in solution. And if water's acidic, we wouldn't be drinking it, right? So this primarily serves as a base, but has, we call it on some certains a conjugate acid just because it's a proton source. That's why we use water for every reaction in acid base, because it's a great source of protons. And we need that for protonation and deprotonation in acid base chemistry, okay? Will he be, what would the question be for this problem? So what would he be asking? For this one that I'm doing right here, the problem could say a buffer containing large amounts of the weak acid HF and its conjugate base F minus is prepared. Please write the chemical reaction that shows how this buffer can remove added hydroxide from the system to prevent a significant change in pH.
So does it matter if you put the conjugate base before the conjugate acid? Or is there...
Order does not matter.
Okay.
Order does not matter. Yeah. You could actually have H2O here and then F. Doesn't matter.
Okay.
Yeah. Yep. Okay. So let's go ahead and just do another thing. So if I give you this, again, we're going to stick with hydroxide so we can practice. What is the conjugate acid and what's its conjugate base of OH? So what's the acid? What's the conjugate acid?
H2O.
H2O. So what do we do when we're dealing with conjugate acids? This means it's what? What do we do to create a conjugate acid?
You add a proton.
Have to protonate, correct. Use this terminology. Okay, conjugate base, what are we doing?
Taking away the proton.
Yep, so we're deprotonating. Okay, now you have to pay attention to charges. So OH minus is like looking like this, right? If we took this away, are we becoming more negative or positive?
If you took the H away.
You're becoming
Yes.
more negative.
So then what would my charge be on my conjugate base?
O2 minus.
Good, okay? Make sure that you pay attention to the charges of these things, okay? Because we already were negative, right? And so he kind of tricks a little bit with this. So just follow your charges, okay? Cool. Let's go ahead and do some, let's do some pKa stuff. Okay. So the biggest thing with Henderson-Hasselbalch, I'm just going to abbreviate this. Okay, I'm not writing that. The Henderson-Hasselbalch equation. Do we know what that is?
Yeah,
That's
the
the one that's like pH equals
Yes.
plus like the HA over A or whatever. A over HA.
Ooh, yep. That's an H. I meant to do an A. So what is this?
That's the base.
This is the
conjugate base.
base, right? Conjugate base. Is it, so it's the conjugate base, okay? And what is this?
Weak
Just-
acid.
Just the acid, right? It could be a strong or, it could be a strong or it could be a weak. It doesn't matter. It's just the acid component. It's the portion that has the proton source, Okay, so the biggest thing about this is we can find two things via the Henderson-Hasselbalch. You can primarily solve for one, pH, right, which most people solve, or two, you can solve for pKa, okay? And that's but you have to be given one of these. So if you're given the pKa, you can solve for the pH. If you're given the pH, you can solve for the pKa. You also need to have molarity, okay? Molarity meaning the concentration, right? Because here we're talking about acid-base chemistry. We're in water, so we know it's going to be a solution. It's not going to be solids, so we're dealing in terms of concentration. Okay, so a question that he could give you is determine the pH. To determine the pH, so you have, I'm just going to make up numbers because I don't feel like doing anything other than that. You have 0.02 molar of this. How should I make that? Because that makes sense. Okay, let me go get my other pKa problems. All right. And we'll do this, and we're gonna go to, okay. Where are my work? I have so much stuff, I can't even sort stuff out. Okay. Is everyone feeling, in the meantime, talk to you guys, is everyone feeling okay for the exam tomorrow? The mini exam tomorrow?
Yeah.
All right. So, oh, what the heck? Something is, okay. So let's say we have, my kid is playing Mario Kart and it's like, I'm hearing Mario Kart in the background. Okay. So let's say we have this. Okay. We have 0.20 molar of HC2H3O2. Doesn't matter what this is, okay? He's giving you the concentration of it. And then we need to calculate the pH of a buffer solution made from this and made from this. What do we see about these things right off the rip? What do we see? Which one's the acid and which one's the conjugate base?
Yeah.
Look for the proton in the front, okay? Even though there's other protons here and there's still protons here, these are not going to dissociate, right? This primary single H in front of everything is really what gives us as an acid, okay? Look for that. So we have, go ahead.
That means that that one's the acid, right?
This is the acid.
Okay.
This is the straight acid. Whether it's weak or strong, I'll give you some key identifiers as to strong acids and weak acids, so you can kind of look at that list and write those down. But anytime there's a single H in front of the solution, please, that's the acid, okay? So we don't have that here, right? So he's gonna give you the concentrations, which, okay, number 3, check. We have molarity. We've got big M's here. We've got 2 of them. We've identified the acid and the conjugate base. Cool, so I'm gonna write here con B, and I'm gonna put here acid. Cool, so we've identified. The next thing we need to have, the next piece of information that we have to have is either something called an acid dissociation constant or pKa. And he'll either put both of those or just say pKa in exam. So the pKa that I'm giving you is gonna be 1.8 times 10 to the negative 5th. That's the pKa. So now all you have to do is plug it in and figure out. We don't have to do any conversions here because we're already in molarity. I have seen him in the past start with grams, and we know we can get to grams for moles via the molecular weight. So if you were given grams, you do grams over molecular weight to 1 mole, and then we can go ahead and get that into moles per liter, right? So you can convert if you were just given grams. You can get that to moles. Because even if we were just putting it in moles, we know moles per liter is still the same thing, right? So you could put it into moles. But I have seen him do that. I don't know if it'll be on the exam, but just know, you know how to convert. So
Liz?
then, yes.
I remember doing something with negative log in regards to the pKa. Is that
Yes.
needed?
So that is for proton concentration. So if you see this, that's only for proton concentration. Like that's a different, yes, the question will give you a pKa. So this is what you're talking about, and we'll get there.
Oh, okay.
This is a different thing when we do 10 to the negative of pKa. Yes, the question will give you a pKa or a pH. The question has to give you two things. It has to give you some sort of information to calculate molarity or give you molarity, and has to either give you pKa or pH.
So if it gives you like Ka, that's when you do the negative log.
Yes.
Okay.
But I have never seen him do Ka
Okay.
on this.
He did it on the quiz.
Yeah, he did.
Yeah, that was on the quiz, which was pretty confusing. Yeah, it was also in the 2 buffer review worksheets under the lab folder.
Yeah, that's like where I found how to do it. So I could still do it. Like I did it fine. It was just an extra step.
Yeah. So that so that's something that he probably did this semester. I've never seen I've never seen it on an exam in the past. So he's probably just doing that because he's assuming that you guys have more time, and he's writing these new sheets. So he's thinking about what to put on it. Remember, most of the time when we're on campus, he's just kind of a plug and play guy. But I think now that he has time to sit down and create new content, this is what he's doing. He's going to make it a little bit more challenging. Okay, so we'll go over that Ka. If he gives you that, you'll take the negative log to find pKa, and we can go through that. But most of the time, you'll have to be given pH, a pKa, and molarity. Okay, in order to solve Henderson-Hasselbalch, you have to have those things. So now in this terms, we're finding the pH. So we'll go ahead and just say that the pH equals the pKa, which we're just denoting that as 1.8 times 10 to the negative 5th, and then plus the log of, and then you just put your concentrations. Okay, so the first concentration, remember following order, it would be 0.50 because that's the base, right? And then we put that over what?
0.2.
Right. Because that's the acid. Do this first, then take the log, then add, so that you have everything right math-wise, and you should get a pH of 5.1. Okay, if I were to do this problem in reverse, let's put that there. And I needed to solve for pH, which you guys could technically test right now. You would do the same exact thing. We would have, so let's say we have the pH, and it works. This is a great way we can do both. The pH in this problem was 5.1, right? So we'll put pH there, equals pKa plus the log of the base. Okay, do this first, take the log, but now we'll have some value there, some value here, right? Equals 5.1. You'll have to subtract that value from here, and then you'll get the pKa, okay? Cool, so you can manipulate this either way to solve for either pKa or pH. So let's take a look at his notes.
Wait, I'm
Can you
sorry.
go
So the
over how
answer
you
to
got-
that was 5.1.
How did I get 5.1?
Yeah, I keep getting 0.39.
That's what I got too.
I got that too.
Did you get these
And
numbers?
I did it both ways. I plugged it all in
Did you get
one
these
at
numbers?
first.
Did you get 0.04? Did you get 0.40 or no?
Yeah.
0.40, and what's the log of 0.40? Or what's the log of, so you got 0.5 divided by 2, it should be 2.5, right? 0.25, or what's the value for this division?
2.5, yeah.
Okay.
The log of 2.5
is 0.40.
Yeah, and then when you add the 1.8 times 10 to the negative fifth, it's the same.
Which is what? What do you mean the same?
0.40 again.
Yeah, I got that again too.
So you have, because, okay, so this, we should take this right here, take the log of this. Tell me what you get. Take the log of 1.8.
I think it's because when I type in just 1.8 times 10 to the negative fifth, I got an error on my calculator, so it's probably just not calculating it.
Log of 1.8 times 10 to the negative fifth is negative 4.74.
Yeah. So
we're supposed to take the log of both the pKa and
no. I just did it, and because I make these problems myself, so I should have taken the log of this. So you can just keep it as this.
pKa. So the pKa is 4.7.
Yeah.
Okay.
So no negative.
Yeah, don't worry. You don't take the log of the pKa. You'll be given it. But when I was doing my math, I left it as this instead of taking the log of it to try and find some good numbers, realistic numbers. So this will be your pKa. So your pKa was 4.7, which makes sense because we're dealing with acid base, so it should be that. It's a weak. So that's perfect. So the pKa is 4.7, so you'll just go ahead. This is 4.7 when I take the log. So then 4.7 plus the log, you only take the log of what your acid is, acids and conjugates. You don't take the log of the pKa. So 4.7, and then so 4.7 plus 0.40, that should give you this, right?
Mm-hmm. Yeah.
Yeah.
Cool.
I have a question really quick because he did this too. Mm-hmm. So like,
let me pull up that quiz.
When you first when he first gives you the molarity of like, and then he gives you like the, what is it? Like the chemical compound stuff, like CH3, whatever. One of them he put like 2 minus, and the other one he just put minus. So if they both have negatives, how do you determine? So like basically, I guess my question is, if it is not a lone H, it can't be like separated.
So he gave you like, are you talking about number 3 where it's talking about H2O4 2 minus?
Yeah.
And H2PO4?
Yeah.
So, okay. So
like the HPO4, would that be the acid since that has the lone, or that one would be, the acid that has that lone H?
Yes.
Okay, I just wanted to clarify because I was getting confused with like both of them having minuses.
No, you don't look at the charge.
Okay.
Oh my God, this stupid little thing. Get that up there. Okay, how to, yes, Lou. So your question was HPO4 minus, right? 2 minus. And then H2, right? PO4.
Yes, just 1 minus.
So this right here is dead giveaway. H2, PO4 minus. Honey, you have to go into the room. I'm in a session. Okay, go. Thank you. So this right here, you just want to look for something that's in front, because what makes something a conjugate is its ability to get rid of that lone H, right? For this PO4 to get rid of 2 hydrogens, that's a lot. Oh, is the quiz? Wait, Shayla said something. Yeah, normally the pK are more like whole numbers in the problems. Yeah, exactly. In the quiz, he just gave you a pH and asked for the weak acid and pK. Is there any way to find pK without knowing molarity? Technically there is, it's on a chart, but you'll never have to do that. So don't worry about pKa without knowing molarity. He'll give it to you. Okay, so yeah, for this, like I said, you have to think about how can we get rid of, what's the easiest out of these 2 to get a lone H? What is the easiest way to find protons and grab protons? Okay. And it would be via this guy, right? Same as this, and same as this, right? Even though we call this weak, we can still strip this. The reason we call this weak, by the way, is because fluorine is so electronegative that he really wants to make the bond here, but he can also survive as just an F-, and he's happy to do so because he's already super electronegative. Okay, so that's why this one is weak and why it's quote unquote special. But anytime you see an H out in front, that's the easiest. And we think about if we looked at the molecular build of this, right, versus the molecular build of this, we already have 2 H's bonded by that. And that's difficult just to go ahead and strip 2 off of these, because he'll just keep them. He'd rather just keep this. This guy's like, okay, I'll give you my H, take away my H. Okay.
So you're just trying to find one that has just 1 H in front, and that will tell you what your acid is.
Yep.
Okay.
1 H. Okay. That's the easiest way to identify it. Okay. So let's go ahead and see what he did regarding your 10, negative 10. Let's see where he put that. I printed off his stuff. Okay. We all know what Le Chatelier's principle is, right? He might ask you that. He might ask you that about it because I know I've seen that before. So what is Le Chatelier's principle?
Isn't it just like when they add something to one side and so it shifts to the other side?
Right. So it's like the disorder, right? It's like the amount it's trying to get to. Are we trying to get to an equilibrium or not with Le Chatelier's?
Yes, you are.
You are, okay. So Le Chatelier's is really focusing on equilibria. And so it's nice to know what that is, because I've seen him put that in a multiple choice. So, and that's how you also determine how an equation, like how an acid-base reaction will shift either to the left or the right, okay? So, and the goal is to produce, like, another person. It's how likely is an equation, a chemical reaction, going to shift to the left or the right. Cool. So let's look at what other quiz things. I don't want to go so much over the quiz because people haven't taken it, and for those that did, it's kind of unlucky. Le Chatelier. Yes, I can spell Le Chatelier for you. Le Chatelier's principle. Okay. Another another kind of terminology you need to know is, I don't know if you guys saw this, but zwitterionic. Did you see that?
Yeah, that was on the quiz too.
Okay. This, yes, I have seen him do it. So what it means to be a zwitterion is that you have both positives and negatives in the molecule. So you could have something over here like this, and then you could have right? So this OH is minus and this sodium is positive, but in general, what is the overall charge of this molecule?
Neutral.
It's neutral. So a zwitterion has to deal with, you have 2 points of a molecule that clearly hold a charge, but together the net is still neutral. Okay, so very important to know that terminology. I was looking through his stuff and I don't know if I saw that on his stuff. But I barely read this.
I've seen that before.
Huh?
I've never seen like that Twitter.
And it wasn't in his Buffers lectures, right? In the sheets that he posted. I don't see it.
It wasn't in his Buffers lectures, but it was on the quiz.
Yeah, on the quiz, but there was no other. How else would you have learned? I'm trying to see if there was any other.
I Googled it, but I never saw in anything that he gave us.
Okay.
About it in lecture 9.9.
Lecture 9.9. Okay, yeah. So basically it's just because I think it deals with a lot of amino acids and stuff like that. We see that. So yeah, a zwitterion is just you have one molecule and you'll have 2 poles that have both a plus and a minus, but together it's still a neutral molecule. But that's a zwitterion. or as bitter ionic bond, right? Or charge. So it just necessarily just still means that you have two poles of opposite charges. And it's not necessarily poles, it's just two portions of the molecule that have its own charge opposite, right? Plus and minus, that makes a neutral molecule still. Could you go over question 5 of the quiz? Like what we would do? Okay.
Also, really quick, can we also go over an example of when an equation shifts to the left or to the right?
Yeah.
Because I really don't get that.
Okay. So via Le Chatelier's, right?
Yeah. Thanks.
Mm-hmm.
Rochelle, there's a really good in our textbook. I've just been using that. There's like a really good chart.
Oh, really?
Yeah, it's table 9.5. I'm not sure exactly what page it's on, but it has like diagrams, and then it says like concentration. If you add a reactant, then the reaction shifts toward the right, and then it just like gives you a chart.
Okay. Okay, perfect. Thank you so much.
Oh yeah, it's on page. If you just go
Yeah.
to like 9.3 chemical equilibrium, it's like that whole section, and there's like a video too.
Awesome. Thank you.
That helps. Yeah, I've just been using that whenever there's a question.
Cool. Thanks so much.
Yeah.
Okay. We can still go over some things too if you want to. Okay. So I think that the biggest thing that you guys need to, let's just first of all give you some verbiage so you can write this down. Strong acids, okay? I'm just going to label that as this. Things that you need to know are strong. Yes, I can go, yeah, 6 for sure. So we can do strong acids, HBr, HCl, HI, HNO3, and then H2SO4, okay? This is strong and a strong acid. And the reason we say that is, you know how last time we talked about it should have a solo H, but this is strong because of its ability with water. So this is kind of, I'm going to star this, right? So we need to kind of talk, we can talk about for certain things in this, and it kind of goes over the quiz and validates the quiz. So then we'll have, so those are just strong acids, okay? Just strong acids. Now let's go over some strong bases. Things to recognize: LiOH, right? This, I would say NaOH, right? This is very important. KOH, okay, are we seeing a trend? Anything that has OH. Why? Because acid-base chemistry, everything comes from water. So those are the most important things to, the other ones, you can have beryllium, you can have strontium, but those are, I would just focus on these ones. Okay, weak acids. Right, so weak acids, acetic. Okay, we have formic. We could have hydrocyanic. Okay, why is this weak? Because of this right here, right? So when we talked about like things dissociating, these are not individually going to dissociate. The CN's going to stay together, but this H might get ripped off, right? So you'd have a CN minus. HF, same thing, right? He can live by himself, but we could still take that proton if we needed it. And then H3PO4, I've seen him use. And so then we'll go ahead and talk about weak bases. And NH3 and NHCO3 and CH3NH2. What do we see constant in here? NH, NaH, sodiums, and nitrogens, okay? Those, when you see those are really weak bases. So kind of trends to follow: strong bases, hydroxides, right? Weak bases, anything with nitrogen or sodiums and carbons, okay? Strong acids will have a H available to them. We'll talk about H2SO4, okay? And then weak acids, remember, they have more hydrogens, but they can also, these dissociate differently. So you won't have a full dissociation. Like this one doesn't fully dissociate because this stays together. This is weak. Why? Because look what's primarily in it. You know what I'm saying? So what's the likelihood of trying to make use of this OH here? And then we're left with just CH3CO. It's really hard. These are okay, but they're not ideal. They're not like decent, okay, to do reactions with. So those are the kind of things that I would pay attention to as far as identifying what's strong or weak, is make these little tiny lists. These are the ones I've seen a lot. I know he likes NO3 a lot, okay? NO3, NO2, he likes to use those as examples. All right, so now let's talk about what should we go over? Okay, let's just take another look at this quiz. That's my quiz. Okay. Okay. So if you have a buffer, you need to make a buffer solution. That's a good question. If we need to make a buffer solution, okay. If we need to make a buffer solution with a pH of 4, first of all, we know that low pH is what? Acid or base?
Acid.
So high pH is?
Base.
What if I had a high pKa? What is the high pKa?
Acid.
Then is a high pKa indicated of an acid or base?
So the smaller the pKa, the stronger the acid. I don't know.
What do we think? Let's talk about it.
Well, doesn't it have to do with the Ka value, and the Ka is about acids?
So yeah, we're all dealing with the amount of the proton concentration. That's what pKa. So if you have, you can think of it in terms of Ka. I just like to think of it in terms of pKa, because going to Ka, you have to take the log and all that. And most of the things that he'll give it to you, like I said, I think it's weird that he gave you, let's look at this quiz, that he gave you Kas on the quiz. He gave you Kas on the quiz? Given the Ka. Yeah. So the Ka, all you have to do when you're given a Ka value, you just take the negative log of that. Blah, blah, blah. You take the negative log of it. It's a pH. That's a pH. pH. So when you're given a value, this is going to be relatively light. It's going to be like this, 1.10 times 1.0 times, it'll be like some sort of stupid thing like this. 1.0 times 10 to the negative 8. And then you're going to take the negative log of that so that you can get to be some value. And these are just made up numbers, so don't think about it. So if he gives you something that looks like this form, and he says that's a Ka, right? You need to turn that into the pKa, and that'll give you more solid number, okay? That's the only time you'll take the negative log of the Ka. So remember that, okay? Negative log of the Ka equals pKa. Then we can use the Henderson-Hasselbalch. Yeah, it's pH equals 4. Okay, so in one of the quiz problems, he gave you the Ka for H2PO4 is 6.6 times 10 to the negative 8. You need to do this first to make it pKa. Okay, so again, if we have a high pKa, the higher the pKa, that means we have a low Ka. Okay, so if we have a high pKa, that means we have a low Ka. And what does that mean? Weak acid or strong acid?
Strong acid.
Are we sure?
Weak.
Let me look. So low pKa, strong acid.
Exactly. So then that means we have to have a what? If we have a high Ka value, okay, then we'll have the higher pKa. So a high pKa is weak acid. So a high pKa, so if we're dealing with a pKa that's like a 10.3, and there's a couple on the practice exams that he's done in the past where he's listed off pKas of molecules, and he said which one of these is the weakest or the strongest. Let's see if I can find it. And so he gave you like 10.32 pKa, 9.2, 4.76, and 7.8. And the question was, which of the following is the strongest weak acid? The strongest weak acid. So this pKas deal with weak acids, okay? pKas, acids, pKas. These are strongs. Now we're talking about weak acids. Acids, weak acids. So if you have a low Ka, you're going to have a high pKa, right? Because we've taken the negative log of that. You're a weak acid. If you have a high Ka and you have a low pKa, that means you're a stronger acid. Okay, higher the Ka, lower the pKa, that means you're strong. It's very contradictory, okay, to what we're used to. It's because this is where people get confused. A high pKa means a weak acid, right? When you are finished, is a low pH a strong acid and a high pH a weak base? Okay, I'll get that in just a minute. So pH is just dealing with the acidity of that solution, right? So to kind of go over that, so low pH doesn't necessarily indicate if you're strong or if you're weak. It just categorizes you as an acid or a base, okay? So that's all that this is telling you, is based on the scale from 1 to 14, if I'm a base or if I'm an acid. This is going to tell you, pKa is going to tell you whether you're strong or you're weak of that group, right? So remember how we were talking about bonding and we said there's hydrogen bonding, ionic bonding, covalent bonding, and I told you that there's forces like a subgroup. This pKa is like a subgroup of acid base. So acid base puts you into an automatic category, and then the pKa component will tell you a subcategory, whether you're going to be a strong or a weak acid, or a strong or a weak base. And then based on that information, you can decide which base or which acid you're going to use via Le Chatelier's principle to manipulate the reaction rate. Are we clear?
So it's like, is the Ka like a measure of the proton concentration pretty much?
Exactly.
Okay.
So you have to differentiate based on pH, right? I'm going to erase this since nobody needs it. Exactly. It's starting to click now. So pH, you need to decide if you're first an acid or a base, okay? And that's what pH does. And then the pKa focuses on the amount of proton source, which does the reacting in acid-base chemistry. That's all we're doing is pushing protons. So then you have to decide if I'm a weak acid or if I'm a strong acid, and if I'm a weak base or I'm a strong base, right? And we've given you lists of that. And then you can go ahead and pick, okay, well, if I have a strong acid and a weak base, who's gonna favor more? Am I gonna favor the products or the reactants based on what acids or bases I use, okay? So they're like levels. This is just categorizing you into what? This is telling you which one would be better to react. Who's most likely gonna give up a proton source? And what can I use that would serve a better proton source? Like this versus this.
So pKa is only measuring acid.
It's not just measuring acid, but it's because we're talking about bases here. It's measuring proton concentration.
Okay.
Was this kind of based off of number 5 on the quiz?
Yes.
Okay. I know the answer, but can we just go over that? Because I'm still trying to look at it and it's just not clicking. Like
Okay, 4, 5.
I just went off of it because, like, I don't know if I did it right, but I knew that like in a buffer, the amount of the weak acid and the pKa and the pH are close to the same. So I like did it that way, but I don't know if like that's the right way to do it. But I just picked because it's 3.74, right?
Yeah.
Yeah, so then I was like, okay, that's close to 4.
It's being wonky. I have to. Here we go. All right. It's still loading. It's still loading. It's still loading. Okay, so let's just see what most people put. And this is for the one that says buffer solution with a pH of 4, right? That has an acidic lifestyle. Okay.
Correct.
Okay, so he's giving you, so first of all, he's telling you the pH. So he's telling you it's an acid, right? And that's just the category, acidic lifestyle. Which weak acid should you employ? So you have to know like, so you have to think if we have a pH of 4, right? What the pKa is telling you is telling you the source of proton concentration. And remember, proton concentration plays a big role on if you're an acid or base. So the thing is, you kind of want to look for what is more close to the pH in this case, okay? And that'll give you should you employ. You don't know how many protons are going to shift, but if I had a pKa of 2.12, first of all, is that strong or weak? Is that a strong? If my pKa is this a weak acid? Okay, so this is a strong acid, right? So if I'm taking strong acid and I'm putting strong acid in strong acid, and the goal is to make a buffer, and we need to know what it is to be a buffer. That means we're not moving. Sorry, my handwriting is very bad because I'm trying to use this tablet. We are not moving plus. We are stopping this. The goal is we don't want any more movement of hydrogens. That's what a buffer is. Buffer is just, let's keep it so that nothing is shifting, okay? So if I added something that's strong to an already strong acid in water, we're gonna still have some movement. The goal means that we went to a pH of 4 and we're adding more proton sources, that's my pH, then we're gonna assume that my pH is gonna drop. Okay, it's gonna be more acidic. So is that actually making a buffer?
No.
No, because we're reacting, we're making something more acidic. Now, if I say, let's go ahead and add something with a pKa of 9.2, this is what?
Weak.
And we're putting something weak in an acid, so what's gonna happen here? Which way do you think the equation's gonna shift, left or right? I have a lot.
Acidic.
I have a lot.
Left?
So it's gonna go this way, right? Because the goal is I have a weak acid here. And so what's gonna happen is I'm dumping so much weak acid into something that's acidic. We're gonna try and equal this out, but that's not necessarily making a buffer. Okay.
So is that adding too much weak?
Yeah, you're adding too much. So let's look at our weak acids, right? What were some of the weak acids we talked about?
HF.
So if we had something that had an acidic lifestyle like this, and we're adding HF, but its conjugate would be F, right? N plus H. If we're adding this into this, what's going to happen here? We'll have a bunch more of this and this, but are we really going to see this? What's going to happen to this concentration of hydrochloric acid?
It's going to decrease.
So what's going to happen to our pH?
It's going to increase.
Exactly. Is that making a buffer?
No.
Remember, what is the definition of a buffer?
Has to contain relatively equal amounts of the weak acid.
Equal amounts. So right off the rip, when you're taking a multiple choice like this, look for the extremas. 9 okay, the pH is 4, get rid of the highs and the super lows. The super high pKa's and the super low pKa's based on the pH, okay? He put 2 on there because it's close to 4, but what's even closer to 4 is 3.74, okay? So that's why that answer would be HCO2H at the pKa of 3.74. Find your pKa to be closer to that pH. Less change, less movement of those hydrogen ions. Okay. Not very intuitive because it says which weak acid and everything's like weak acid, strong acid, buffer. But the key things out of that is knowing the pH, knowing that you're making a buffer solution. So you want to keep things relatively similar. Does number 6 on the quiz have to do with acids or bases? In a titration experiment, no, it doesn't. That's titration. So we'll go over that real quick since we're on it, and then I'm not going to do any more quiz stuff. In a titration experiment involving lactic acid, how many equivalents of NaOH are required to reach the endpoint? So you have to look at the molecule, which I know some people said didn't load for them, I think. Okay. Look, how many equivalents of this do I need to add to this to reach an endpoint? So what does it mean to reach the endpoint? What does that mean?
Is that when it's like fully titrated?
That's like done. There's no more reaction, okay? So look at all these OH groups that I have and this. And then this is just a methyl, right? So we would say that's a C and then H3, right? There's 3 high and then there's hydrogens here. So is this going to react?
No.
Is this going to react? Think about what we're reacting.
Yes.
Would this react?
Yes.
Okay, so how many equivalents are required to add to put this into to reach the endpoint? So I want you to watch out for this, okay? What is this functional group? Yeah, okay. So when you have something that looks like this, the likelihood the reason we talked about functional groups is because we need to identify them. This is sterically hindered, okay? You have 2 hydroxyl groups next to each other. So in order for this to take place, do you think that this OH is gonna rip off and this is gonna become a sodium? Do you think sodium could take this place to make water? So really, what is the only reactive spot here?
That one OH.
This one. Okay, so the only thing that could happen here is I only would need 1 equivalent because this is already a carboxylic acid. It's going to stay this way and it's not going to really do anything. And even if it were to take this H off, what we could form is we could form something that looks like this, but we would have this again. And then what's going to happen is you'd have H2O in solution plus sodium. Okay, and then it's just going to go ahead and rip and make another OH. So this is not going to do much. This is your only source of reactivity here. Don't get confused by chiral molecules cannot be titrated. That is, chiral molecules are actually really important because they're 4 different substituents, and so there's more opportunity to kind of interact. But this carboxylic acid, you only would need 1 equivalent. You don't need to saturate. Plus, this is what we just realized.
Strong base.
It's a strong base or is it a weak base?
NaOH.
A weak one. Oh wait.
It's strong, right? I have and now I'm getting confused. It's strong.
Is it?
Yes.
Yes.
Okay, good. That you have to be familiar with these things. So I'm just making sure I know. So NaOH is very strong. So when we have a strong base and we have what is OH? What is OH? Weak or strong?
Strong.
Is this strong? OH is a strong acid. This is a strong acid. So we have, this would be the base, and this would be the conjugate, right? Okay. Is that the conjugate?
Conjugate base?
Is this the conjugate base or conjugate acid if I have H2O?
That's the conjugate acid.
So then what would be the conjugate base of this? See how easy it is to forget when we're dealing with conjugates? So remember, if I have this.
The HO minus?
So hold on a second. So if we have water and we're treating this.
It would be O-2.
This would be what? O-2?
That would be the conjugate base. Right?
So if I have H2O and I need to deprotonate it, because we're trying to take away when you deprotonate, you're making it what? An acid or a base?
Base.
Okay, so H2O, if we take away one H, then we would have what?
OH minus.
Okay. Right? We take away that, we'd have OH minus, and if we added
H3O.
Yes. So adding protons is doing what?
Making it an acid.
Correct. Making it an acid. Taking away protons is doing what?
Making it a base.
Correct. Okay, so let's go back here. If I have OH on this terminal group, if I have an OH, what are we saying this is? What are we going to denote this?
The conjugate base.
The conjugate base, but we don't really, in general though, would you call this an acid or a base? Would you call this? I would call this a base, okay? Here's why. Here's why I would call this a base. This is a very, 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 very important to know. I would call that OH a base. Why? Because what you just told me, where it's derived, okay? What you told me is you said that H3O plus is a conjugate acid. And you're telling me that this OH is derived from water, okay? So I've clearly lost an H from my derivative. This is the derivative. I'm derived from water and I've lost an H. So I have to be what? I've lost an H. I've been deprotonated. So I have to be what? A base, okay? And then we have a strong base and a base. So we're using what? NaOH, and we have an OH. So how many equivalents do I need to do? I only need one equivalent because I'm dealing with base and base. So for that problem, it doesn't matter how many equivalents you fold, there's really nothing going to happen because you're adding a strong base with base. So what are you doing? Nothing really in that equation. Okay, all you're doing is adding one source of proton. So he had like 1, 3, 2, or whatever, and then nothing. You only need to add one, because what are you adding to your molecule here? You have two functional groups that consist of OH and OH, and the main thing that you're adding has OH. So all we're doing is stacking up base on more base with more base. So really, it doesn't matter. To finish the end, you only need one equivalent of that, because of everything that's else is on this whole molecule. You don't need to add any more than that because it won't do anything. Are we clear with how that works?
So does it also work if you use the molecular ratio? Like if you were to write out the equations?
Given a molecule? What do you mean write out the equation?
Yeah, so I just wrote on the quiz when I was doing it, I wrote out the I don't know what it's called, what is in lactic acid.
Uh-huh.
And I added NaOH and then I balanced it, and then the molecular ratio was 1 to 1, so that's how I got 1.
You could definitely do it that way.
Okay, because that seems a lot easier than trying to figure out like the weak acid.
Oh, lactic, yeah, so lactic acid is this C3H6O3, right?
Yeah.
Plus NaOH. So let's balance this and figure out what things would react. So what's going to do the reacting here? What would be my products?
H2O.
And
then it's like, let me see how they met up. With NaC3H5O3.
so we triage this, right? We know this is the reacting part, and this has so many hydrogens. So we would have what? C3, you put Na?
Yeah.
3, H,
and then O3.
right? So it just stripped one from here, plus water. Okay, so then if we go ahead and balance this, what do we have? Do we have anything that needs to be balanced? No, right? Everything's equal.
Yeah.
1, 1, 1. So you could do it that way. Absolutely, you for sure could do it that way. And it would be clear as long as you knew what these molecular formulas are. Sometimes he'll give it to you and sometimes he won't. So that's why it's nice to remember like acetic acid, because he'll use this one a lot. So, but yeah, this is perfect. No balancing needed, so you know the ratio is 1:1. Therefore, you'd only need one equivalent. But the same thing goes for when you can look at the substituents of things, right? And we know we've got the carboxylic acid going on here. And because we're adding more of this with it, all we're going to do is we only have these two spots. The only thing we can make is H2O, and it's just going to keep doing that. So we only will need one equivalent because it's just going to keep doing the same thing no matter how much we add. You don't need to do any more. You don't need to oversaturate it. Okay, 1:1 ratio. But this works good as long as you know the molecular formula of the stuff, which you're all on the computer, so I'm sure you could look it up when you take your exams. Okay, number 2 on the exam, on the little preview quiz, was compared to its cousins, HCl, HBr, HI, HF is unusual in that it is a weak acid with a pK of 3.14. At physiological pH, which of the following statements is true? So they're talking about, in this case, physiological statements is true. So we have HF has a pKa of 3.14. So is this concentration equal to this concentration?
No.
Why?
Because the F minus like lost the hydrogen.
Right. So in terms of pH, what's happening here?
Or increasing.
Is this pH high or low?
High.
There's no proton source here. So is this pH high or low?
High.
So if there's low pK, then it's strong acid. So it has a low pH?
Low pKa equals strong acid. Is that what you're saying?
Yeah.
I want you to think of terms of proton source. We have no proton source here, and protons are what make us acids and bases. So if I have no proton here,
basic.
Exactly.
Okay, so since
not let charge scare you, look for protons, H's, follow the H's. So if I have no H, I've gone from something that is a weak acid to now more basic. So at physiological, it's saying HF is unusual and that is a weak acid with a pKa of 3.14, which at physiological pH, what's physiological pH?
7.
Cool. At physiological pH, which statement is true? Okay, so we have that, we have HF. So this is a strong, it's not, it's a weak acid because a lot of people think it's a strong acid, but it's on the strong acids list, but I've put it as, actually, no, I didn't put it on the strong acids, did I?
No, you didn't.
Okay, HF is, even though it looks like it's strong, you have to think on the periodic table, fluorine can survive like this because he is so tight and wound like this that losing this H is really is not detrimental to him, even though he wants to be like in the noble gases and be an have all of his fulfill the octet rule. He's unusually weird just because these things can easily dissociate. So when we're talking about in terms of acid-base chemistry, what is easily to dissociate? And this is weak because he's willing to give this up right away. He's not like holding on to it. So you could take that off. Strong ones are going to do the ones that are going to do the grabbing. So this guy in general, he's either happy like this or he's happy like this. He can be happy either way, which makes him weak. Okay. So in terms of like, I think we should also justify or define what is the definition of a weak base or a weak acid so that we can get a little bit more of like a clear concept. So we have to talk about dissociation. I'm going to tangent for a minute and then we'll get back to question 2. You have to talk about dissociation. Okay. So a weak acid is something that partially dissociates. Okay. Partial dissociation, meaning if I had a bunch of HF in solution, that maybe 50% of them would dissociate, right? Like maybe these ones, and then these guys will stay together, okay? When we have a strong acid, you're gonna have full dissociation. So that's why when we see this, when you see hydrochloric acid and stuff, you will see this fully dissociate. So you'll have, you'll see these, and plus water. What are we making in water here? What do we do if we add hydrochloric acid with water? What would we make?
H plus and Cl minus.
So this will go into H plus and Cl minus. If we add this with water, what's going to happen?
H3O and Cl minus.
Yep. Yes. This guy is going to leave. Okay. This is more inclined to separate and fully dissociate than HF is. Okay. So again, a weak acid is an acid that will partially dissociate into its ions. Partially dissociate because it could stay like this, but it could also live like this. But who's to say which way it's going to go more so? That's why it's a special case, right? Only about 50% of these are going to split. In contrast, the strong acid will fully dissociate into all ions in water. At the same concentrations, weak acids will have a higher pH value than strong acids. So just because, remember, if it's a weak acid, you'll have a higher pH just because you don't have that full dissociation. So now we have concentrated hydrogens together still in that HF form. So still in this acidic form, we'll have this, but then we'll also have this, right? So if you don't have full dissociation, your pH is still going to be relatively low, or a high pH rather than a low pH. So pH is also based on the concentration of hydrogen atoms, but we don't really use it in that term. That's why we use pKa to determine concentration of hydrogens, okay? pH to just determine if you're an acid or a base, and then we're gonna go ahead and say, and remember that's level scaled, right? So you can say, okay, well, if I have a pH of 5 and a pH of 3, then you can kind of scale it and say, okay, well, I know that the pH of 5 is a little bit more basic than my pH of 3. So which one of those is more acidic? Right? So we use that as a general scale, but in terms of proton concentration, you need to look at your pKa's. And just know about dissociation, which one is more likely to fully dissociate. Okay, HF does not fully dissociate. HCl does, HBr does, 100%, but these guys do not. It's the only case, and that's why he's a weak acid. Okay, so back to our question on that quiz, because we're kind of jumping everywhere. We have HF equals F minus. We have HF is greater than F minus. So if we have the constant, if we have a pKa of 3.14 and at physiological pH, so if this pKa is 3.14, what do you think our pH is going to be? What do you think our pH should be of a solution? What does this mean again? Okay, so what do you expect our pH to be? High or low?
Low.
Okay. Low. Okay, so let's just say right now we're at a pH of 3. Okay, so if I add more, so we have the first option is, wait, this is less than, right? So if I have greater than, if I have more, I'm looking at both. If I have more HF, so more acid, technically weak acid, because F minus is the conjugate base. If I have more acid, am I going to have a high pH or a low pH with more acid?
Low.
Low. So is that getting me close to a pH of 7? No, so it can't be that HF is greater than F minus. We can't have more acid if our goal is to get more basic. Okay, so now if I have less acid and more of its conjugate base, so more F minus floating in solution, will that get me closer to my pH of 7? Because now I'm trying to put it in its more basic form. So my pH should be more basic, right? That is going to change the concentration, pKa. If I take away those protons, I'm expecting to create a higher pKa, which means I'm a weak acid and I should have a higher pH value, which gets us closer to the 7.
So on the question, I guess I'm just a little bit confused as to like, I get how we got like the weak acid and the base, and then I just get confused because there's no like real answer. So are we just trying to get it to be a buffer? Like we want it to be as close to physiological pH, or like what?
You don't want to think about it in terms of a buffer, because buffers, how I think of buffers, it's like stop the reaction. Buffers for me, stop the reaction. Okay, we're not moving protons. That's what the use of a buffer is. Because if you put a buffer in something that the protons are ready to jump around, they're going to do that until all of the protons are where they need to be, and then the reaction is done. But if I put a buffer halfway in there, then I'm stopping those protons from moving, and then maybe I could take some solution out and take what is there and do another reaction. The point of a buffer is to just stop things at halfway, 3/4 way, or whatever, just stop the movement of protons. In this question, you have to think of it conceptually. I know pKa, a low pKa is a strong acid. So with the exception of HF, okay? So they're saying that is weak, okay? So we have to, in that thing, you just have to think about, okay, if I have a low pKa, which this is, and I want to get to something that's more basic, knowing that a low pKa is more acidic, how can we make something more basic? And in this case, you want to favor the base. Add more base to become basic. So in that question, you have to identify, you have to know that the HF is the acid and that the F minus is the conjugate base. And in order to go from a low to a more basic solution, how do I do that? How do I favor that?
Okay.
How do I favor that, right? And I think he just uses wordy stuff like it's a weak acid with a pKa of 3.4, but we know that low pKa's are strong, right? That's why he likes using HF, because it confuses you guys. And he keeps saying weak acid, weak acid, weak acid. Well, Liz told me a high pKa is a weak acid. Yeah, you're right. But he likes HF because it's unusual. It's still very electronegative and it only partially dissociates. So you can still have moments where the pKa is 3.4 because HF did not dissociate fully. So you still have some HF and then you'll have H and F. Does that make sense? I have a solution. I'll still have HF together, but then some of it dissociated into H and F. So this part is going to do some reacting, but this is still making it acid, right? So how do I make it less acid? I have to add more base. I have to add more F. I have to saturate it with F. So that's why the answer is HF has to be less than the F minus. You have to get rid of that part that doesn't dissociate. Okay?
Okay, that makes sense. Thank you.
Mm-hmm. HF is added to toothpaste. Anytime you see stuff like that, please ignore it. I don't even know. That doesn't even, no, doesn't make sense. HF is fluoride. It's fluoride. Okay. What else do you guys want to cover on here? What do you want to do? We can do a couple more problems, and then I'm going to let, is the exam in the same format as the others? It should be. The answer was HS, yes. HF is smaller. Yes, HF is the acid. So we have, ignore pKa right now. Just ignore the pKa, okay? One more time, ignore the pKa. If we have an acid and we want to get more basic, how can we get more basic?
Add more base.
Add more base. So now let's look at HF. HF is the acid, and based on the Henderson-Hasselbalch, the conjugate base would be F minus. So if we're looking at those three options, if we need a physiological pH of 7, okay? You don't even have to look at the pKa at this point. If we need a physiological pH of 7, and we're sitting at something that we're going to assume is acidic, right? Because even if it's a weak acid or a strong acid, those terms, just get them out of your head right now. Those just are used to indicate how more likely is the proton going to rip off from the one atom. So what is the likelihood of like the H getting stripped off of the fluorine, right? The fluoride ion. That's what weak or strong acid means. So if I need protons right away, I'm going to use HBr because I know that I will fully dissociate all the HBr, which is hydrobromic acid. I will fully dissociate all those HBRs and I'll have a crap ton of free floating H's. But with HF, I might only get 50% of that. Okay? So if I really need a high source of protons, I need to have a strong acid, something that will fully dissociate so that I can reach an equilibrium and have my reaction go faster. If I have a weak acid and I'm putting it in a solution, I'm only going to get partial dissociation, and that reaction might not take place right away. It might be really slow. Okay? Is that helping a little bit better? So you don't really have to look at the pKa in this. I think he just threw that in there to kind of confuse you. I have an acid. Hydrofluoric acid is still an acid, okay? Still an acid. If I have an acid, and I know acids have a low pH, just looking conceptually, has a low pH, and I need to make it more neutral, how do I make things more neutral? Ready? Tell me, how do I make things more neutral?
Add a base. Add
base. So based on those questions, A, B, or C, which one is showing you're adding more base? HF has to be less. The amount of the acid has to be less than the amount of the base. Okay? So that's how you would triage it. You don't even need to do any math.
Could you quickly go over, this is just like the very basic stuff, but like I've always gotten confused about like, so if you have like a base and then you put it into like an acidic solution, does it become positive or negative? Like those type of questions, because I struggle with that a lot.
So if I repeat it again.
So like if you have like a base and then you put it into like an acidic solution, would it become positive or negative, and vice versa if you put like an acid into a base, or an acid in an acid, base in a base? Does that make sense?
Yeah. Okay. Okay, let's see. Okay, so let's start here. if like is going with like, if you're dumping more like with more like, and let's just say these have an overall charge, then what are we doing? What do you think is happening to the overall charge?
It's getting put together.
Right. So is there a change in charge here?
No.
No. No change. And the reason is because all we're doing is adding more something that's positive into something that's positive. So you're just saturating. You're just saturating it. So nothing really happens here.
So if you put an acid into an acidic solution, the charge on the acid would be negative.
So if you put an acid, so this is an acid, and we're putting it into something that's acidic, right?
Yeah.
What happens here?
It just stayed the same.
It's just staying the same. All we're doing in this particular, all we're doing in this particular instance is doing what?
Nothing.
Just adding, yeah, you're just increasing the hydrogen concentration, right? The ability to have more hydrogens in solution because these are acids. You're not really changing anything as far as charge goes. But if we're taking base, which is this, and we're adding it to the acid, what's happening here?
So the base is going to accept the proton.
Right. So so if I have a base over here, which is a negative charge, and then I have protons over here, what's happening? I'll put it in terms of a problem. What would be here? Okay, so in terms of, we have a positive in it, we have this is what? And this is what?
The acid. So it would become positive.
Exactly. So now it's not that it becomes positive. What happens to that? What happens?
The OH like loses.
This OH gained a proton. So what's his overall charge now?
Neutral.
So in terms of positive and negative, really, that's where Le Chatelier's principle comes into. We're not really, when you have the same charge and you're adding it to more charge, you're going to stay in that charge. Same thing. If you have more acid and you're adding the acid, you're going to stay in the charge that you're in. Okay.
So,
but the goal of acid-base chemistry is that we'll become find some sort of equilibrium. And in an equilibrium state, what do you think our charge is?
Neutral.
Neutral.
So is an amino acid negatively charged?
But what?
Is an amino acid negatively charged?
Yeah, and amino acids are a little bit differently, but they're also where the zwitterion comes from. So you could have an amino acid that has a positive and a negative charge and both poles. So you could have like a cysteine has a negative charge or a histine has a positive charge, but together they're negative. Those are just indicating what's going to react here. So I would have more of a base attack this, and I would have an acid attack this. Right.
So if you put glycine in an acidic solution.
So you need to know what is glycine. Like, is glycine positive, negative?
I'm going off a question on the quiz. I know we didn't want to go over anymore, but I was just trying to like make it a basic question to just go over everything, but now I'm just getting really confused.
Okay. So let's see how he wrote that. I don't want
to. Because if you put the glycine in an acidic solution, it becomes positive. But then we were saying that if you put an acid in an acid, it's just.
But you have to. So where is that? I don't see that question.
It's question 4.
Okay. But look at glycine.
So like the OH, that's going to be negative, and then is the NH2 positive?
Yeah.
Okay. So then how do you determine which one it will like attack? Or like, I don't know.
This is the negative. So our pH is 2, okay? The charge on the amino acid will be, so we're already in what type of solution?
So we're already in acidic, which
means what is in solution? What should be in solution?
More.
Some sort of this stuff, right?
More protons?
Uh-huh. So what's going to happen is if there's a proton, you just have to think, you don't have to think what's in solution, just know there's a proton source. So if there's protons here, what's going to happen to this guy?
It's going to leave.
Okay, it'll form water. And then overall, what's going to happen to this whole thing?
That one will just stay positive.
Uh-huh.
Okay. So acidic has high proton concentration. Basic has low. Okay, I need to put that down. Okay.
Because remember, we talked about it. If you're dealing with this,
so amino acids are kind of like tricky ones because they're the Zwitter ones. Okay. But if it was just like not amino acids, then it would still relate to like the acid would stay, would no change and would stay negative. Okay, that makes sense.
Correct. And that's where he that's where terminology is important for that. Yeah. So again, we have this, right? And then this would be the conjugate acid, and this is the conjugate base. So, yeah, acid will have a proton source. And so every time you're in an acidic, yes, we can. Every time you do an acidic, in an acidic solution, you just have to think of it in terms of, I have a plethora of this. So what is going to happen with these that are free floating? Okay, get off of hydrofluoric acid. Get off of it. Think about just in general, if I have any sort of acid, what is going to happen? I have dissociation occurring. I have a lot of hydrogens. Those are ready to attack. And what are they going to attack? Okay. And in that case of that Zwitter ion, you had the sodium. Anytime you see sodium, please know he always has that. And then you had whatever, something like that. This is reactive. This is going to go and pick up this. Yes. Okay. All right, so I have some requests. We'll come back. We'll do one more. We'll do a last minute review on acid base right before we sign off, because let's let our brains rest. But let's just go over some people want to go over chapter 7 because the exam's tomorrow. So let's just do a few of those if everyone's cool. Is everyone cool with that? Yeah. Okay. Let's review this. Let's review some graphing. Let's talk about temperature. Let's talk about volume. Let's talk about pressure. What would go down here? If we're talking about, if we want to relate, let's relate this one, V and P, so volume to pressure. And let's do pressure and temperature, and let's do volume and temperature. Okay, so what would this graph look like? What's going to go on my x-axis? Pressure. And what's going to go on, perfect, and what's going to go on my y-axis? Volume, right? So how is this graph going to look? Linearly, exponentially, and explain why.
Exponential.
So where am I going to begin?
At the top and then like go down.
Okay, why?
Because as the volume increases, the pressure decreases.
Right, think about a jar. If I have big jar, all my molecules are like this. If I condense the jar, I'm creating more pressure, right? Those molecules are closer together. So we should expect as the pressure or the size decreases, and the volume decreases, say right here. Yep. So as soon as the the amount of volume or space decreases, my pressures automatically increases. Cool. Let's do this one. Pressure and temperature, where should I put them?
Pressure on the y-axis, temperature on the
Pressure. Okay, and how are my graphs gonna look?
linear going up.
This way?
Yeah.
So as I increase my pressure, then my temperature increases, or as I increase my temperature, pressure increases,
Yeah.
right? These will both increase. Okay, what about volume and temperature?
Volume on
A
the
negative relationship.
So what happens if I do what? As volume increases, what happens to temperature?
it decreases.
Decreases.
So how should I draw my graph?
Going down.
This way?
Yeah.
Okay, are we all in agreement?
Is volume and temperature directly proportional? Is that what that means then?
Yes, these are directly proportional. Linear relationship, directly proportional. Okay, so that is very important to realize. But conceptually speaking, we need to know that temperature will decrease as volume increases. And I use the example of a boiling water. You boil the water, you left it on the stove too much, all the water evaporated except for a little bit. That was still boiling. You add a cup of water, regular room temperature water. Is it still going to be boiling?
No.
Because not only did we re-increase the volume that was already boiling, we've increased it, but now the temperature's decreased. We've got to wait for that to go back up. So know that as volume increases, temperature decreases. For here, as pressure increases, then temperature increases. Is that what we're saying here? And that this is an exponential relationship. And a lot of it has to deal with just the molecules and the space. Cool. That would probably be something he asks, but more on a conceptual, like the syringe problem we went over. Okay, math parts. Let's talk about, do I have any new math problems? I don't know, I have so many things, let's see. Okay. Let's talk about, I did a bike one with you, right? We left off on number 5. Okay, so number 6, draw the graph. We kind of just did that, right? The syringe, but we can just redo that. If I have a syringe, all right, and I'm talking about the volume of gas that's trapped in the syringe as it changes on pressure, we just talked, so here's my volume and here's my pressure. What's gonna happen? It should look like this, right? So as we push on the syringe, not only are we losing volume, but our pressure is increasing because the molecules are being forced to funnel in less space and then through the size of the needle. So this is how the graph should look. Number 7, which of the following statements about intermolecular forces is true? Remember, bonds equal molecules, forces equal atoms. Okay, between molecules, 5 in the equations. Oh, multiple choice, 5 in the equations. Okay, so you want to deal about molarity? Okay, so determine the molarity of a solution dissolving 4.4 grams. Okay, but I just want you to remember this part, okay? Forces are between atoms, bonds are between molecules. Please know the 3 types of bonds. Please know the types of forces. Start on 6. Okay, calculate the mass percent of a solution. So let's go ahead, mass percent. We have 17, we're on the review that I sent to everyone. Okay, 17.2 grams of NaCl, and we're putting it into 149 gram of water, 149 grams of water. So these are in the same. So what do we do for mass percent? Where do I begin?
You just divide solute by solution?
Right, solute, total solution. And that's gonna be 17.2 over 17.2 plus the 149. Then you're gonna times that by 100%. That's the percent mass of this, the mass of this. Okay?
And all those units have to be the same to solve.
Yeah. For the most part. Now, sometimes he'll give you like milliliters, but even then I've still seen him solve it the same way. So like he'll say milliliters of water, but it doesn't matter. You'll still add the whole thing. The only thing that you need to make sure is that your solids, so like this is salt, that your solids are in the same units, okay? If he gave you more than one solute, but he shouldn't. All right, next, clear that. So that's 7 or 6. Number 7, what is the molarity of a solution? Okay, so this is a dilution problem. So we got to deal with, we have 125 mils. We're diluting 125 mils of this 2.50 molar NaOH to 575 mils. How do I do that? The goal, what is the goal? What is the end goal?
The molarity, so moles over liters, so you first you need liters.
Right. What is molarity? That is the end goal. So where do I begin?
You could start by converting to liters.
What equation would do I need to use an equation?
No, just, I mean, 125 like to 1,000.
Okay, so you want to convert these to liters. Okay, so the 125, is that what you want to do?
Mm.
What is equal to what?
0.125.
Mm-hmm. So then what do I do?
And then now you would do the 2.5 divided by the 0.125.
But what is that going to give me?
And then you'll have X over your converted 575 milliliters.
So so you want to do this first, right?
Oh, yeah.
And then, but so what equation are we using? Are we doing, because we have, what are you using are you using an equation, or are like trying to look at like?
I guess I've been using the M1V1.
Exactly. That's what I was asking. That's what I wanted to look at. Okay. So let's go back, guys, and make sure that when you're doing this, what equation should we be using? Does this look familiar? I mean, I didn't write them subscripts but are we familiar with that? Because we're trying to find the new molarity given this dilution factor. Oh. Are we clear with that, what it's asking?
What is that? Anyone's like law?
It's just, I don't think so.
Okay.
I don't think so. I think it's just concentration. Okay, so we have so then this would be our M1, right? And that's our V1, and we need to transfer this into liters, right? Are we agreeing?
Yes.
So would we actually need to divide these? Are we dividing these things, or are we multiplying?
No, I made a mistake there.
Okay.
Because it'll be 2.5 times the
So,
one.
yep, so 2.5 molar times the 0.25 liters equals M2 times the 0.575 liters. And then go ahead, multiply first, then divide by 0.575. And that's going to give you your new concentration. Cool?
Is that equation specific to dilution?
Dilution, yeah. A lot of it has to do with dilution.
Okay.
Because when you're diluting, you're taking something of high concentration and you're trying to bring it to a lower concentration. So that's what we're trying to solve for, is concentration in dilution problems. Good question. Okay, good. What number was that? That was 7, right? Okay, what is the molarity of each of the following? What is the molarity of each of the following? So we have 750 milliliter solution containing, did anyone get 0.103 for number 6? What'd you guys get for number 10 for number 6? The mass percent. I didn't do the math.
I got that, except for you have to times it by 100%.
Yeah. Yep. Multiply it by 100% for number 6. So it should be what? Okay. So in this one, we have 750 ml solution containing 2.10 moles of Na2SO4. You're welcome. And then, so let's start here. How do we go about, what is the thing that we're trying to figure out? Again, what are we figuring out? Molarity. Okay, which equals, so what are we given? This mils. So what do we do here?
Liters, convert to liters.
Yep. And we have moles. So do we need to do any conversion here?
No, just moles over liters.
Okay, so then you just go ahead, and the only thing we had to do in that is just convert milliliters to liters. So you should have this, and that'll give you big M. And I did do the math. I think I got 2.8. If we have time, can we go over number 5? Yes, I'll circle it, Shayla. Okay, is that cool? Did we get that?
Yes.
Okay, it gives you a lot of information, but really that's all we're figuring out. You just need to know this equation. So let's do another one. We have 1 liter solution, but we're given 25 grams of NaCl. Now what do we have to do? What's the difference here? Instead of converting the volume, what do we need to convert?
Grams to moles.
Right, so let's do that. What is the one thing that we need to convert grams to moles?
Molecular weight.
Molar ratio.
Molecular weight. Molar ratio comes from equations, balanced equations, okay?
It's on the periodic table, right?
Yeah, so periodic table. So what do we get sodium's molecular weight to be?
58.44.
And that, oh, dang it, it's doing it again. I clicked it. This stupid pen. And the math department gave it to me because I'm a TA for calc, and 58.44. And so I don't like this stupid thing they made me up. Okay, here we go. 58.44 grams, right, of NaCl for 1 mole. And that gives me what? How many moles?
0.43.
0. Point what?
43.
43. So then what do I do? That goes over 1 liter. Make sense? We don't need to convert. We're already done. Any questions? So I would just make a little side note when you're practicing, how do we convert moles via grams? We have to use the molecular weight. So we'll do grams over molecular weight to moles. And then for concentration, right, when we're dealing with concentration in terms of just volume, you have to just make sure you do milliliters to liters. That's the biggest thing, okay?
Sorry, so I was gone for part A, so that one you just convert, like you said, milliliters to liters, and then.
Yep. So in this case, just first that identify your units. Okay, I gave you moles in the first one, but I gave you milliliters, so you've got to convert the milliliters to the liters because we know that big M, which is molarity, is moles over liter. So you just have to make sure that you've got this going on. You have liters and moles in the situation. And he'll easily switch those up. So you'll have to just do one dimensional analysis, one conversion.
And for the molar weight of NaCl, did you just add the weight of sodium and then the weight of chloride?
Mm-hmm.
Okay.
Mm-hmm. Yep, just add weights. From P table. Okay. All right. So let's go on and we'll do some more. If we have time, can we go over number 5? Number 5 on the moles molarity calculation, right, Sheila? Is that what you're asking? We can just do that really fast before I forget. Determine the molarity of a solution by dissolving 4.45 grams. Okay, so determine the molarity. Molarity, again, is what we're doing. We're solving for molarity of a solution by dissolving 17.2 grams of NaCl in 149 grams of water. Oh, wait, I'm reading the wrong problem. Guys, this is bad. Why didn't anybody stop me? Nobody stopped me. You're horrible people. 4.45. Oh, God. 4.45 grams of potassium chloride, okay, in the final volume of 150 mLs. Determine the molarity. How do I begin this?
Convert milliliters to liters.
Okay, so what do we notice right off the rip about this problem?
We have to convert 2 things.
2 things need to be converted. So we'll start with the volume. It's always easy. So 150 milliliters. Equals what?
0.15.
Okay. Cool here? Now what do we have to do with this? First of all, you have to know what potassium chloride is. That's potassium chloride. I've given you an easy one to figure out. There's no balancing. You don't have to worry about anything. I've given you something on the left hand and the right side of the periodic table. So you should be familiar with kind of putting words in to making molecules. So that's potassium chloride. So we need to figure out, what do we need to solve to get to moles when we're dealing with grams again?
Molecular weight.
Molecular weight.
Cool beans. So what is the molecular weight of potassium chloride?
$74.55
grams
per mole.
Yep. So now what value do we get? I guess I could do it, but I don't feel like it. I feel like this is better.
We get 0.06 moles of KCl.
0.06, right? Okay. So then all we do is put it into what the formula for molarity is. So 0.06 moles KCl per the liter of solution. And that will give you your molarity. So the other problems I made you only have to do one thing. Here you have to do both things. Okay? Are we feeling a little bit more comfortable with this kind of stuff?
Sorry, I think I'm getting the 150 is from the problem before. So how do we finish this? It's the 0.06. That's what it is, the moles.
So it says determine the molarity of a solution by dissolving 4.45 grams potassium chloride in the final volume of 150 mils. So the total volume is 150 mils. You have to convert that to liters because molarity is moles per liter. So convert that. So the goal is 0.06 moles over the 0.15 liter, and that's going to give you your final answer in moles and molarity concentration. That's
thank you.
Whatever this is. I didn't do the math, but that's the total concentration. Okay. All righty. Let's go ahead and keep going on here. We have a few left. So how many grams of insulin are present in 26 grams of a 0.45% molar solution? How the heck do we begin to do that? And what is this question even asking? Do we even know?
I think it's asking for mass percent.
Mm-hmm. So how do we do that?
The solute over solution.
The 74 grams per mole T is from the molecular weight of sodium chloride. Okay, all right, 26 grams. So mass percent, right? Are we looking for mass percent? So if how do I go ahead and start this up?
Wait,
again?
which problem is this one?
We're going on number 10.
Okay.
How do we start number 10?
You're gonna put the grams of the solute over the grams of solution.
Okay, so we do what?
Oh, okay, this is reverse. So you would do 0.450% is equal to, and then like X over 26.0 grams, and then solve for X.
Do we agree with this? Kenny? I see some people texting down there. Is this what we would do?
Yes.
Okay, so then how would I go about solving this?
You would multiply by 26 on both sides.
Okay. We good? Any questions? So when you see things that look like this, it's a mass percent. It's a mass percent problem. So remember, you can just go ahead and do it backwards. Work this equation backwards. M divided by M. Okay? Are we confused on this one? No? Yes? So I gave it to you in the problem. I said this, M over M, right? So you just work backwards, solve for something, divide it out, and then multiply by the grams. Are we confused? Would that be 7,200? What's our solution? What's our answer here?
11.7.
That's what I got.
26 grams times 0.450% equals what?
11.7
grams.
Yep.
And that's grams of solute, right?
Just the insulin. Forgot the decimal, thanks. Yes, please watch your arithmetic. Can we do number 9? Again, more mass percent. Number 9. Yeah, we can do number 9. So calculate the mass per volume of the solute. So if I have 25 grams of KCl in a 50 ml solution, what is the mass per volume for the solute of each? So how do we go ahead and start this?
You would convert to liters for the 50 ml, I believe.
Well, for mass per volume, can't that stay in mLs?
Mm-hmm.
Oh.
You don't have to. You don't have to. But I have seen people do it. So if you want to, you'll just have to make sure that it makes sense in your final answer, because we're trying to find a percent here. So this would make it relatively small, right? So you can. It doesn't really matter. It's unnecessary. So how else would we do it? How else would we solve it?
2.5 divided by 2.5 plus 50.
So 2.5 plus 50 equals what?
52.5.
And then if we took 2.5 and divided it by 52.5, what do we get?
0.05.
Yes. So in this case, guys, when we're figuring out mass per volume, it doesn't matter your units, okay? Because it's just dealing with mass per volume. This can be any unit, this can be any mass. The only time that we convert is if we need to get into something specific like concentration, right? Where concentration is only measured in liters. In this case, you don't have to do any conversion. So we would have 25 or 2.5, I'm sorry, there's a decimal here. Now I'm forgetting my decimals. 2.5 over 2.5 plus 50. 52.5, 2.5, approximately 5%. Okay? Cool. Yep.
Oh, and then we have to times by 100, right?
Wait, so in part B then where it says 7.5 milligrams, you wouldn't have to convert it to grams on that one either?
No. Okay, so we're having issues with this and the insulin one. Okay, we have 26.0 grams and it's 0.450%. So when we worked backwards, what value did we get? Did you guys keep it in a percent, 11%? Those that solved it?
As the answer?
Yeah, what did you get for the answer? Because remember, the answer should be grams.
Yeah, 11.7 grams of insulin.
Is it 11?
We left it as a percent.
Wouldn't it be 0.117 grams of insulin?
Yeah, you left it as a percent. If you're getting the 11, you've left it as a percent, okay?
Oh, okay.
So it would be this many grams.
Okay, thank you.
Yep. Good catch. Everyone's doing the right thing. 0.11.
Then you just divide by.
Yes.
100.
Because you're already given the percentage, so you got to divide that out. Yep.
Okay.
Which you guys just didn't. You left it in the percent form. Cool. So let's do the second one, which is casein. In milk, we've got 7.5 milligrams of casein protein in 1 milliliter of milk. So how do we go about starting this one? We're trying to find the percent mass per volume. How do I do it?
You're going to do milligrams of solute over liters of solution, so we have to convert milliliters to liters.
If we convert, if we converted that, so we're going to start with milliliters. You want to convert this to liters?
You don't need to convert it.
Yeah.
Yeah, I thought for mass volume, we didn't need to convert it.
Exactly. So don't worry about converting here. We don't have to do any conversion in mass volume. Okay?
But isn't this parts per million?
If it's asking for parts per million.
Are we on 11?
9.
Oh gosh. Oh, sorry.
9. No, yeah, we're just finishing up 9 again because I had some people want to go back over it. So we're dealing with number 9B, the casein. So where do I go? How do I start this?
You need to convert milligrams to grams.
Do I?
No.
7.5 over the milliliters.
Okay, so then what would I get?
Wouldn't it be like 7.5 over 7.5 plus 1?
What do I get?
I got 88.2%.
Now, does that make sense?
Feels like a lot.
So in this case, we have to think about, though, milligrams. Here's why people right off the rip want to convert. Milligrams is really small, right? Compared to grams.
Mm-hmm.
So we have a tiny amount, tiny amount. And so we shouldn't be having a huge percentage number like this. So if we got 7.5, because this is in milligrams, all right, and grams, what would this be in grams?
0.0075.
And then so if we did that grams and we converted these to liters, we would have what?
0.0085 liters.
Right? So the thing here is when we're dealing with these milligrams to milliliters in this problem, this is the one that this is one that he put on the test, and it's tricksy. You really don't have to do any sort of conversion in this way. Milligrams to milliliters, we treat that as a 1-to-1. So how would I go about getting this percentage? How do you think I'd get this percentage? How could I get 0.75%? You tell me, how do I get that percent?
Well, wouldn't it be 7.5 divided by 10 times 100?
10 times 100?
I just did 0.0075 times 100, and that got me 0.75.
0.0075, right? Because we're dealing with a 1 here, okay? So even though we're used to adding these things here like this, we're treating this as in terms of just the casein in 1 ml of milk. So on the problem, oh yeah, I just scrolled up, oops. So in this case, this is the tricker part, and this is the softball that I put this on here because this was on an exam last semester. This one, you would just have it be it's just treated as times 1. You don't need to add another equivalent, because that's like for the whole, when we do this, we're doing it for the whole entire thing, and we're giving you that there's 7.5 milligrams in 1 ml of milk, right? Not just the whole thing, ml of milk. Like we're just dealing with a fraction here. So this is a tricky problem, and I'm glad like I said, I'm glad I put it on here. In this case, you would just have to move that decimal over and you get the same amount. So it would be 0.75%. Don't expect this to be there. I just know I've seen it before. I've seen the same thing, and he copies and pastes it. Copies and pastes it. So if you see that, it's just the same answer. Okay, what else do we need to go over? I don't remember what question we left off on. Can somebody remind me? 10, 11, 11?
11.
Yeah.
Concentration in ppm, parts per million. Okay, parts per mil. All right, so we have a solution containing 1.50 milligrams of copper in a 100.0 milliliter of tap water. How do I figure this out? Where would I start?
We need to convert milliliter to liter.
Milliliter to liter? Do we all agree?
Well, when we're thinking of concentration, should we automatically think of the molarity?
Should we? Should we?
That's how I was gonna like figure it out. But.
Okay, let's triage. Why is that? Why is what? Why is that what? A 1-to-1? I need a little bit more specific question. Sorry, I'm responding to the chat. Okay, so walk me through how you would solve it.
Well, I suppose I would solve it like any other mole over liter.
So you're thinking of it in...
Yeah, that's what I was wondering. Like when I see concentration in a problem, is that where like my mind should go?
Yeah, but in a way, but he wants you to keep it in parts per million.
Oh, right. Okay.
You know what I mean? So how could we do this?
I would take 100 mLs and convert that to liters. So it would be 0.1 liter. And then I would do 100 or 1.50 milligrams over 1 liter. Or 0.1 liter, sorry.
And what do we get?
15.
Okay. Why would we do this? Why would you put the milligrams over the liters? Why did you think to consider converting this to liters?
Honestly, I just looked in the textbook and it says to put milligrams over liters.
Right. So when you're dealing with a parts per million, it's always milligrams over liters. Okay? Parts per million. So remember this. You can go ahead and keep that in. That was a very truthful answer. Most people like to BS me. But when you're dealing with parts per million, it's always going to be milligrams per liter. So you'll get 15 parts per million is the answer. The only thing you'll convert is the liquid. Okay?
Wasn't there like another equation where it was like grams of solute over milliliters of solution times 10 to the 6th?
Yeah, and that's just your conversion factor, because what's 10 to the 6th?
No idea.
In math terms?
Isn't that a million?
Uh-huh.
Just keep moving the decimal.
So, right? So that's how you get parts per million, because they just used a conversion factor to put it in parts per million. That would do the, yeah. So yeah, you can do it as that. So you said it would be like something like this over 1,000. What do we say? 1,000 or 100 milliliters times 10 to the 6th. Yeah. Right. Is that what you're saying they showed in the book?
Yeah, they just put, grams of solute per milliliters of solution times the 1 million, which is the 1 times 10.
Grams. So yeah, if you're given grams and milliliters and not milligrams, then you would do times 10 to the 6th, right? It's the same thing. That's just how you can get it when you're dealing with grams over mils. So milligrams over liters will give you ppm. And then if you're dealing with grams and milliliters, you can multiply it by 10 to the 6th. That's the millionth to go into parts per million. Okay, because all it's doing is accounting for the weight, the decimal changes between grams and milliliters, and then milligrams and liters, right? So here, what's an easy conversion for us to turn it into a liter. But if you're dealing with grams, you'd have to multiply that out. But what could we do here? We could easily take this grams and turn it into milligrams and reverse this, so you don't even have to memorize this. I would focus on this.
Yeah, because you can just convert.
Yes,
grams
exactly. I would just worry about this and knowing that this will give you parts per million versus having to memorize the 10 to the 6th scientific notation. Okay, alrighty. Let's go ahead and deal with, I don't think stock solutions are going to be on the exam. Okay, so today I'm not going to go ahead and the sitter is making my kid be annoying. Sorry. I don't think I'm going to go over stock solutions. I think that those kind of concepts are going to be more conceptual because it's related to dilution. So let's just look at number 13 really fast. If I have a solution that's 2 liters, okay, if I have a solution that's 2 liters, or how would I prepare a 2-liter solution of 1 molar concentration of MgCl2 from stock of 5 molar. So we have 5 molar and we have 1 molar, right? So we have 5 molar stock and we have 1 molar of MgCl2. And the question is, how do I prepare this? How do I prepare a 2 liters of 1 molar if I'm given 5 molars of something? So what you'd have to think about is you would need how many, we have 2 liters. All right, we need 2 liters total. And it doesn't tell you how many liters we have here. It's not pertinent. It's not worry about it. So in order for us to get to dilute this to 1, how many folds, how many liters, each liter is 1, think about it as 1 liter is equal to 1 molar. So if I have a 5 molar stock and I want to get to 1 molar stock, how many 1 liters do I have to add to get this down to 1 mole?
You have to take away 4 liters.
4 liters. I have to take away 4 liters to equal 1 mole. Are we clear on how that works? think of everything as a dilution of tenfold or onefold, right? We call it tenfold in chemistry because it's by usually parts per million or grams or milliliters or stuff like that. So I call it tenfold, but each one is getting diluted tenfold, right? So X, Y, Z liters, so many liters. So I have 5 molar stock solution. If I add 1 liter of solution, that would make it 4 molar. If I add another liter of solution, that would make it 3 molar. If I add another, that would make it 2 molar, and another would make it 1 molar of diluting. Each time I add it, I'm knocking away 1 molar solution. I'm taking away 1 mole of that solution for every liter I add. So it's saying that I would need to have a 4-liter solution to dilute. I would need 4 liters of this, 5 molar, to dilute it to 2 liters at 1 molar. Okay? 4, because I 2 times. So every liter, that's 2 liters and 2 liters. So I'd need to have 4 liters of solution to dilute it to 2 liters at 1 mole. We make sense of that?
So you need to add 4 liters of solution, not take away.
So let me draw it in the picture because some people are really clear with that. I have this, and in here is 5 molar. Okay, and the goal is I want to have 1 molar. So that's the goal. So if I have water and I'm bringing in liters of solution, okay, I would have, if I added 1 in here, add 1, this is basically saying 5 minus 1. Now we're at a 4 molar solution. Over here is my tallies of liters that I've added. I've added 1 liter, right? And now I'm at a 4. If I add another liter of solution, now we're at 5 minus 2 equals 3 molar solution. So there's another liter I've added. If I add another liter of solution, now I'm at 5 minus 3 liters, which equals 2 molar solution. Okay? If I add another one of those liters, now I'm at 5 minus 4 liters, which gives me 1 molar. So to make 2 liters, so I've added 4 liters here, right? To make, how would you prepare 2 liters of 1 mole? Now do math. If it takes 4 liters to make 1 mole, then I can easily say that 2 liters plus 2 liters equals 1 molar. So really 2 liters each time, because that's 4 liters. I'll need to make a 2-liter solution will give me 1 molar of solution. I've added that. Does that help? Does that clear some air?
Yeah.
Okay. So you just need to go ahead and think about how many times am I adding mils to decrease that. I don't know if I'll have that be on the test, but it's nice to know because he could associate it to a dilution problem.
So the 2 liters doesn't really have any significance.
Nope.
Okay.
Nope. Nope.
I kind of just have a basic question. Sorry, you can finish that.
Yeah, and even so, if we had a 4-liter stock solution at 5 moles, and we just keep adding that down, you would still get it that you'd need 2 liters.
Okay.
Yeah, go ahead. What's the question?
So when he says, or when they say in the book, like dissolves like, is that based on the attractive forces only? So you have to have the same attractive force?
Like dissolves like. So when I talk about like dissolves like, I kind of talk about it as like, when you're given a situation, you want to look for things that are similar. So like if I had product, like these things are similar because they all have this group. So it's not necessarily about charges. It's just what would be more inclined to do the dissolving. Another way to look about it is like in sort of or lipids and fatty acids. So if I have something that looks like this, and then I have something that looks like this, and then I had something that looks like this, right? And then, but my main backbone was this. If this was which would be more inclined out of option 1 or 2 to dissolve in this? If we needed to dissolve something in this lipid, what would be more inclined to dissolve in that lipid? This, number 1, or number 2?
1 in every 1.
Number 1, okay? Number 1. Everyone's gonna say number 2, but what is this OH gonna react with in this line? These are all happy. Everyone is happy. So I don't have anything for this OH, this hydroxyl group to react in a carbon chain. Think about it in terms of like layering oil, right? That's why oils, if you like had a pot of water, in the case of this problem here, water would be like the NaOH, and oils, this would be an oil and this would be an oil. If I had a little pile of oil and I added more oil, it's just gonna make a bigger round of oil, right? And it's all gonna be together and the water's still gonna be down here. That's what it means by like dissolved likes.
Awesome, thank you.
Okay, so yeah, it's just when you have things of similar backbones and similar structures, they're more likely going to blend in and mesh together than something that has other functional groups that are not like the chain, the original chain, the original molecule. Okay, anything else that we want to work on? I think that for advice, sorry, I gotta run your nose. As far as advice goes, today is Thursday. When is the buffer quiz due? Tomorrow, right?
Yeah.
If you guys have questions on that, go ahead and privately email me. I think personally, I know the weekends suck, but I think that if you're not sick of me, if you want to have another session, we can do this weekend. But I need you guys to come because my material is getting really light. We're like doing same problems and it's hard to make content and they don't pay me enough. But if you guys want to bring me problems, I have no problem meeting once this weekend, whether that be Sunday. Saturdays are a little bit weird because people want to do, do have some free time. But if you guys want to do like a little micro session, study session Sunday because your exam's Monday for 8 and 9, I'm cool to do that. It's just up to you guys.
Yeah, Sunday works.
Does Sunday work for everyone?
Yeah, Sunday would be great.
Yeah, Sunday would be good.
Because I think that'll give you enough time. We kind of hit the quiz today and I feel so bad. I wish part of me was like, man, I should send them a message. Don't do the quiz. Because at first he said that the quiz was going to be due Wednesday. And so I'm like, I don't have time to hold a review. But then I saw that it was on the 4th. And so I was hoping that you guys would either try to attempt it once and save your last attempt. And then we could talk about it. But I didn't get out fast enough. I didn't get out to you guys in fast enough. So for those that didn't take it, you're in luck because we did a little review today. For those of you that did already take it and didn't do well, just know it's 6 points. It won't affect you because there is extra credit at the end when we do our capstone. So you're still fine, okay? Don't worry about it. But I think then we should just meet on Sunday. We will not do any more molarity. We will not do any mass percents. We will not do any of that. We can stick straight to 8 and 9. Buffers, acids, and bases. Sound good? And then I'll just kind of pull up extra stuff from the past. I think I have some extra stuff from tests.
What time are you thinking on Sunday?
Whatever works for you guys. I'm available. I'm available anytime. So it's really what
maybe so we can have like the rest of the day to study and over things.
Sure. Look, he gave you equation sheets for the exam already. Yes, I will, T. I'm doing that right now. Or we can stay on as soon as everyone leaves and I can walk through it on the whiteboard with you. Your call. Yeah, yeah, whatever. Does the morning work for people? And what time? Because I don't really want to do 8 o'clock. I don't want to do
I like 11 or like 10:30 wouldn't be bad.
10:30, 11?
I think 11 works.
11?
11 is good.
11
on the
would be
chat,
good.
on the chat, everyone just put it in. Oh, yep. I'm seeing. Okay, good. Seeing. Good. Okay, good. Yep, great. Okay, by default, let's shoot for 11. I'm gonna send out another invite now. You'll all get it in Canvas. It'll be for the review. I should send it to everyone just so that they know. Strictly 8 and 9. So if you have molarity questions, things like that, privately message me. I don't want to spend time going over it. We're going to hit acids and bases, give your brain to like settle what we learned. Make sure you understand pKa's and stuff. We'll hit it hard 8 and 9 on Sunday 11. Sunday 11. Got it. We'll do it. Okay, any other questions, comments, concerns for anyone?
Thank you so much.
Hey, you're welcome. Okay, look for the invite.
Will the test all be multiple choice, or is it going to be like?
It should all be multiple choice.
Yeah. Okay, thank you.
Yeah.
And then one last question. You're thinking that tomorrow's will probably be around like 10 questions, right? Like 2 points each, you said?
I'm okay. I am more than likely thinking that's what it's going to be like, because I haven't seen it yet, but I'm assuming yes, because it's still out of 60 points. He's just broken up into 2 tests, and usually every question is 2 points. So I'm thinking there's only going to be 10 questions at 2 points.
Okay.
Yeah.
Okay.
If that could have maybe 12 questions, but he's like the kind of guy that doesn't do that. That's too much work. So I'm going to assume shoot for about 10 questions.
Okay.
Let's see if I can see it on.
And then one last thing.
Uh-huh.
Maybe you go over this Sunday, but I'll still look at it, look for it in the book. But can we go over, I don't know how to pronounce it, Lechatre's principle? And it's the left and the right.
Yeah, of course, Le Chatelier's. Yeah, that's just, I'll briefly tell you right now what that focuses on is Le Chatelier's is the amount of disorder and the likelihood that something will move left or right based on the concentration. So we can definitely cover that. Let's just say if we have a lot of acid on the left-hand side and we have a lot of base on the right-hand side, then, or not a lot of base on the right-hand side, then we need to drive that acid to the left, right? So it just depends on how much do I add in my products or reactants that will force this equilibrium.
So if we have a lot of acid on the left-hand side and then not as much on the right-hand side, we would need to drive that acid to the right-hand side.
Yes, and how would we do that? We'd have to dump base in our product, in our reactants, so like water, so that those two could dissociate and create substantial products on the right-hand side. You guys are all welcome. You know what I'm saying? So you would have a lot of acid, you've got to strip, that's a lot of proton source. You'd have to have a base so that we can equal that out. And so Le Chatelier's is what can we do based on concentration to make these things more favorable to creating equilibrium. Okay. If I'm heavy on the left and I need to get to the right, I've got to decrease that concentration on the left, and only doing so by adding base or by adding acid, right? It just depends on what we're looking at. And same thing on the right. If we are heavy base, then we need to add more acid so that we can break up that base and create an equilibrium.
Okay.
And we can cover that for sure. Definitely, I'll put that on the notes.
Okay. Thank you so much.
Hey, you're welcome. Who's still in here? All right, T, are you still in here, T? Let's go over that quiz really fast. Let me read your email. Okay, let's see what we got here. Where are you? There it is. Okay, on the Zoom, we were talking about, okay, clear drawings. We were talking about, can you hear me? Are we good? Can I talk about it in here really fast? Okay.
Yes, please.
Okay, so let me read. On the Zoom, we were talking about exercise during the quiz. You mentioned that HPO4. Okay. Okay, so yes, this particular thing, right, if we think about it, if we have H2PO4 and then we're going to HPO4, so I had a hydrogen and I lost a hydrogen. What is this in terms, if we lose hydrogens, so I'm going to say minus H, what is that? What does that become? Right. And in this source, even though, and this is the tricky part, that's why I started on the strong acids page when we went over strong acids. So I think what I may have confused a little bit of people about is if this were the acid. So we think in general, when we see H plus, and I'm just going to put a variable X here, when we see this, we think, okay, this is automatically the acid component, any single H plus an X, right? But in this case, since we have H2PO4, we're like, okay, well now there's 2 hydrogens and that's not what we're used to seeing this format in, right? But you have to look at what products he gave you, and he's still keeping it in terms of phosphoric acid. Okay, so if we look at this just right away and we see that, okay, just in terms of hydrogens, don't even worry about this stuff. In terms of hydrogens, I had 2 hydrogens and now I'm down to 1 hydrogen. If we just look at that alone, we can differentiate which one's the acid and which one's the base, right? If we just look in terms of H, doesn't matter the quantity. Because even if I was just given this to this, we can still say I lost an H, so I'm more basic, right? This is the structural formula for most acids. It's some H plus some atom, but with HPO4, it goes the same way. So on your question, you're right. If we plugged it in, you should get the 7.8 because this should be the acid, right? And then this is going to be the base because we need to just isolate and look solely at H source. And that's all acid-base chemistry is. Look at the H source. If I'm adding hydrogen or if I'm taking away hydrogen, what is happening? If I protonate, what am I doing? If I'm deprotonating, what am I doing? Okay, and this is how you need to look at it. So when you get these molecules like that, ignore all the garbage stuff and just look at the protons. Did I gain or did I lose? And then you can go ahead. So you did the answer via your email. Your thought process on the latter half is 100% accurate. Follow the hydrogen source and see what's happening, right? We still have it. We still have this same thing, even though it's H2. We still have a loss of a hydrogen. So this would serve the acid base because it's donating. This is accepting. Right?
Okay, thank you.
You're welcome. Any other questions, comments, concerns for those individuals that are still in this? I think everyone's just kind of here.
Could you go over pKa again?
pKa? Yeah.
Yeah.
Quick real thing on pKa. What about pKa? Like
so pKa is the proton concentration, right?
Only, yes. And it looks like this.
And it applies for acids and bases?
Yes, because that's how something becomes an acid or a base, is based on what happens to the proton, right? So if I have hydroxide and then all of a sudden he becomes this, what happened in this term? He gained an H, right? He gained a proton. So he was protonated. He went and he protonated himself.
So why is a low pKa a strong acid?
So a low pKa, why is that strong?
Yeah.
Okay, because this is pKa and Ka are related, right?
Okay.
So if I have a low pKa, then what is my Ka? What should be my Ka?
High.
Yeah, it should be high. So a low pKa, so with the exception of hydrofluoric or fluoric acid, HF, with the exception of that, if we have a low pKa, we're saying we should, this is technically what, weak? Does anybody know what the My Life assignment is about? That's the capstone. So you'll get, that's a capstone.
And what do we have to do?
So you'll basically go into the book and find a couple of topics and write about it.
When's that due?
Right before the end of the semester. And honestly, guys, it's very easy.
Okay.
So easy, and there's any offers extra credit.
So in the book, it says that Ka is the acid dissociation constant, right?
Yes.
And so then the pKa is the opposite of that? So like how much they stay together?
So,
sorry, I'm still kind of confused.
No, it's okay. I don't like, okay, so in your mind, personally speaking, you can think of, okay, let me see if I can think of an easier way. So pKa and Ka are the same exact thing. It's just mathematically different. So I will write this as this is this. This is this, just difference in maths. So we're still thinking about an acid dissociation constant. This Ka will usually be presented to you at something like this. Okay. And that's really nasty to work with. So what we do is we just take the negative log of that, and then we'll get some nice number. Okay. So that's easier to work with because we can see if this is a weak pKa, or a low pKa versus a high pKa, is almost the same as talking about pH. That's why we create a pH scale, right?
So if it's a low pKa, that means that it's a higher Ka, so it has like a higher dissociation constant, which means that there's more H's in the solution.
Yes.
Okay.
Yes. Low pKa, high Ka. High pKa, low Ka. All about dissociation regarding hydrogen source. How much more likely is it to strip the hydrogens off or to use that acid as a source of hydrogen? So like, let's for instance think about, I think the pKa of water is 14, right? Well, 15.7. So if we think that the pKa, if we have a high pKa, what does that mean about our Ka? It's low.
Okay.
So if this is water's pKa, what does this mean in terms of dissociation? Good or bad?
That it doesn't disassociate that often.
Exactly. And when it does, it highly reassociates, right? And that's why we constantly see stuff that looks like this. We kind of always see it like this, O-, but it always goes like this and the arrows are double drawn because it's just constantly burp, 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 just constantly doing it in such a manner that we really don't have two separate things of OH and H in solution. It's just that.
Okay.
Together. Yes.
Thank you so much. That actually really helps.
Really? Good. I'm glad.
Yes.
Anybody else need anything before I go and have lunch? Shayla. People are emailing. Are we good? So we'll plan. I will send it out. Don't look for it like right now. I'm going to go break. Let's go ahead. I'll send out an email with the Zoom invite for Sunday at 11, and we'll just focus on acid base. So in the meantime, take your quiz, take today off, take your quiz, and then we'll go over. Okay?
Okay. Thank you so much.
All right. You're welcome, guys. You'll get it. It'll be fine. We'll do it. We'll kill it. All right. Let's stop recording.